Okay, so let's start. Maybe some more people are connected in next few minutes while I am talking. Good afternoon to everyone. Welcome to the third session of NABIAM scientific lectures. I want to shortly introduce NABIAM just in very few or in very condensed matter. NABIAM is a Czech-Austrian Indirect project. The goal of NABIAM is basically to stimulate cooperation between research institution and companies, and also in companies, company to company, let's say, in the field of nanotechnologies, biosensing, and additive manufacturing. My name is Pavel Kulha. I work as a scientist at Profactor. We are coordinating this project, and we have two other partners. One is on the Czech side, University of South Bohemia as a university partner, and the third partner comes from Upper Austria, which is BISAP, which is a company for business development in the region of Upper Austria. We, as an NABIAM, as a consortium, we are organizing several activities, several events. Unfortunately, all the events had to be online due to the COVID crisis, which happened last year and at the beginning of this year. So we have organized already two series of scientific lectures on nanotechnologies, biosensors, and precise measurement. Second was in February on COVID testing. And this is basically the last scientific lecture, which is focused on additive manufacturing. Yeah, one of the tasks is also preparation of competence map, including infrastructure, equipment, and available technologies that we can maybe connect some institutions and companies. Institution has certain infrastructure which can they offer, and the industry can be interested in this. So for this mapping, we basically organized or we want to organize three webinars. Two of them already happened. One was on nanotechnology, one on biosensors, and one was originally planned actually for tomorrow, but this is postponed. I have to change it also in this presentation, and it's also postponed to September. So this event will happen in September. So I will also send you an invitation that you can also join this webinar. There is also online matchmaking event which is happening next week. This is basically organized as a business to business meeting that companies can discuss about possible cooperations, about possible use cases, and so on. But it's not limited just to companies. If you have something interesting, please register at this web page and try to find a possible peer which you can discuss with which you can discuss your topics. So feel free to register. There is still time. Currently, we have like 40 participants. We would like to have more, of course. So feel free to register also to this event, which is organized by NABIAM. And of course, part of NABIAM is preparation of a joint project for either funded project within national agencies or through European programs. And for this, we are looking for partners. So look at our web pages and contact us if you are interested. So this is again announcement of the virtual networking event, which is 29th and 30th June, basically next week. So look at this web page or our social media or LinkedIn or web page, where you can find also those information and where to register and how. So this was very condensed matter from my side. Today we have scientific lectures which are focused on additive manufacturing. And let me introduce the first speaker, which is Libor Beránek. He is head of Department of Machining, Process and Planning and Metrology, Faculty of Mechanical Engineering. And he's from Czech Technical University in Prague. So, Libor, the floor is yours, and you can start with your presentation.
Thank you. Sending greetings to Southern Bohemia and Austria also. So I'm not sure that my lecture is too much scientific, but we will today speak about 3D printing of metals, some practical applications, and we will start with some basic functioning or functional principles and also a little bit of history. So today we will be speaking about additive manufacturing of metals. Can you see the presentation correctly now?
Yes, we can see it well.
And I had to start the presentation with something maybe a little bit controversial, but we will be celebrating almost 100 years of history of metal 3D printing, even if we don't think so, because 3D printing is perceived as something I would say very new, like 10 years, 15 years of history. You can see that first patent basically regarding the 3D printing. Of course, they didn't call it 3D printing back then, was in 1926. And it was the patent aimed at the use of electric arc as a heat source to generate 3D objects, depositing molten metal in superimposed layers. Basically, this emerged within the time of the construction of skyscrapers in the United States, because the workers spent their whole day and the trip to the highest floors took them maybe half a shift. So they figured out that they will be basically living there for quite a time. And because they were welding all these, I would say, big constructions, so they were quite skillful. And they figure out that they can use this welding technology to make 3D objects by this, I would say, placing individual welds where they need it. And they basically made some teapots and stuff like this. So in principle, we have used these technologies also today, maybe in more advanced fashion, but I wanted to start in this way, that we didn't revolutionize anything, that the skill was here 1926, it was patented, so maybe even sooner. So we are speaking about 3D printing as something which is quite new. We also, it's, I would say, quite good to see the past development, because all the basic principles, or a lot of basic principles of 3D printing today, are connected with the welding, which is a quite old technology, or is it connected with the sintering technologies, which is again connected with powder metallurgy, maybe 30, 40 years back. So a lot of these principles we use today were known quite a long time. If we are supposed to differentiate between the technologies, maybe the biggest problem is that the development in 3D printing technologies is so quick, or in additive manufacturing, that there are, I would say, technologies emerging maybe each year or each few years with using new principles. Sometimes even they are using the same principles, but just bearing the different name, basically as a result of marketing purposes. But regarding the metal 3D printing, we can start with a different source of the material we can purchase. So basically, we can today start with the wire, which is a very common material from the welding. So we can use a wire as technologies which are connected to it are direct energy deposition, where we can basically point the wire in the place where we need to add the material, and then we can use different energy sources to melt it and to basically weld it. And different energy sources, meaning we can start with laser, we can use plasma, we can use electron beam, we can use also traditional arc technologies like metal inert gas or metal active gas. So this is one way where we can get to the metal objects. Second, I would say, form in which we can start the material with is the powder. and then we usually speak about powder bed fusion. So of course the material in the form of the powder is more costly, I would say, than in the form of the wire. So that's something we need to have in mind, because the technologies to make wire are mass production for quite a long time, so we can do it quite efficiently. Basically all the big companies started with the production or some bigger production of powders in the last 10 years. So there is no 50 years tradition of making powders or in some mass scale. So again, when we start with the powder, we can basically use different form of energy. In this case, we usually use laser or electron beam, or we can bind the powder together with some kind of binding agent or bonding agent. So then we can speak about binder jetting. When we use the powder and the energy source in the form of laser or electron beam, we already obtain the final part. So we have the final part with the geometry with certain properties. When we use technology which just connects the powder particles with some kind of binding agent, we can use this as a binder jetting, or we can use this in the form of the extrusion. A lot of technologies for FDM can work today also with metal materials. So then we have a part in the state where there is still high percentage of some kind of polymer or binding agent, maybe 80–90% of the powder of the metal. And then we have to add the process of sintering, where we basically get rid of the organic material with very high temperature. And because there is usually something like 10–15% of this binding agent or material which holds the powder together, the parts during the sintering changes their dimensions quite significantly, again 10% and so on. So this is the technology which is very close to metal injection molding, which is again quite old technology. So this is just, I would say, some general description of the technologies. So we can start when we want to print metals with the wire, or we can start with the powder, and we have different ways how to print the object. Another, I would say, idea I wanted to project here is that every emerging technologies can be described or basically is governed by this Gartner hype cycle. It's quite an old phenomenon which was described already. When you have something new and you don't have enough information about it, you usually inflate your expectations. So I remember myself 10 years ago, maybe 12 years ago, automotive companies were speaking about printing the whole chassis of the car and stuff like this, because the less you know about the practical application, the less you know about the disadvantages of the technologies, the more you are prone to basically inflate the expectations. So when 3D printing became a thing, everyone was speaking about how this will, I would say, replace traditional production technologies. And now we are coming through this era of disillusion, because we already have 3D printers in the industry, in the universities. We work with them, and now we can also see the setbacks, the disadvantages, what are some limitations. And we are searching now in this, I would say it's called a phase of disillusion. I would say we are already here, and we are starting to search for this plateau of productivity. We are starting to search for the application where the 3D printing makes sense, where it's also economical. That's basically the first thing we have to think about when we think about any production technology. We had to think about the economy of the process, because there are many production technologies available, and usually we are searching for the ways how to make things in most efficient way. So this is again something that needs to be reflected when we discuss 3D printing, because I would say the less you know about the technology, the more or the bigger are your expectations. But once you start to use the technology. Once the technology is disseminated in the companies, in the universities, now you will start basically to also see the setbacks of the technologies, and then you have to think carefully about the applications which are reasonable. And today I would say we are quite certain that additive manufacturing is another production technology, and it will be here with the other production technologies for years to come, and it will not be able to replace those. There are few aspects that are very problematic to solve regarding the 3D printing, maybe even impossible. What is the biggest advantage of the 3D printing? When we take a 3D object, which is quite complex, but we cut it into two-dimensional sections. Basically, we will cut this very complicated object with 2D sections. We will get very simple images. This is something that I made with my children at home. So we started with 3D printing, I would say, quite early. And the basic principle is that we can reduce this complexity in 3D into the 2 dimensions, where the object can be easily made by just movement of 2 axes when it's FDM or DMLS technology, or basically with 1 picture if it's, for example, SLA or DLP technology for polymers. So this is something which is a great advantage of 3D printing, that the complexity of the part is not such an issue when we are calculating the price of the product. So we can have quite complicated parts and the production costs will not be so expensive. So this is basically the first chart, or this is the idea behind the first chart here. In conventional manufacturing, usually the more complex is the part, the more costly is the production process and the more costly is the part. In additive manufacturing, the costs are progressing with much smaller, or the progression is much smaller. It's not a flat line, the costs are not fixed, because still the additive manufacturing, the printing process is not the final step. Usually we have some kind of post-processing, and the post-processing is usually more complicated, the more complicated is the product. So this is why this is rising a little bit, but usually the conventional technologies are much more expensive. But we have to see also the other side, that there is a very limited room for cost reduction in additive manufacturing because of the production times. Usually the production times are on the level of hours. When we are discussing printing metals using powder bed fusion, some of the prints we made were 70 hours, 120 hours. So we are discussing days or sometimes even a weeks of process. And then the depreciation costs are quite significant costs for the part price itself. So there is smaller, I would say, potential for cost reduction for the additive technologies. So when you start to speak about serial production, then you have very small room to optimize the process, to reduce the costs or the times significantly. And usually if you want to build up capacities, it means that you have to buy more of the machines, buy more production technology. Then of course the depreciation costs are again growing. On the other hand, when you use basically machining, you can use different technologies of machining, which are quite cheaper than the additive manufacturing. Or if you really want to go for mass production, today basically the whole automotive industry, whether it's plastic, whether it's metal, so you use injection molding or high pressure die casting. So you use technologies which are quite expensive when you develop them, when you build these technologies for specific parts, because you have molds which you have to make that are quite expensive, you have some production equipment, but then the production times are on the level of seconds. The time cycle for injection molding is usually within seconds. Time cycles in high pressure die castings are on the level of minutes, maybe 2 minutes, and you have the engine block for personal car or for in automotive industry. So then the production costs are quite or significantly lower than the costs of the 3D printing. You have to invest a lot to make this process efficient on the beginning, but when you have a product which will be made next 2, 3, 4, 5 years, which is typical, for example, for automotive industry, then you have the options how to make even complex parts very efficiently. So this is the second chart. And then the additive technology within the mass production has its limitation regarding the price. So basically, when we are speaking about any technology, we have to see the advantages. I would say I have mentioned basically all of those because we have some limited time. I will not be speaking about those in such a detail, but I would say the general idea behind it was already mentioned. And we have also some kind of disadvantages because we usually work with some kind of heat which is induced into the production process, and we work with materials that are, I would say, normal materials. They are having some coefficient of thermal expansion, so their geometry is changing with the temperature. The residual stresses are affecting the geometry. We can connect, or we can quite easily compare the additive technology to the casting technology. But on the casting technology today, when we have good molds, we can get the specification within the under a millimeter, within, I don't know, half a millimeter or 2/10 of the millimeter. But with the additive manufacturing on the same size of the part, you are usually struggling with millimeters. Then we have another issue, which is a surface quality. And the more productive additive technology, the worse, I would say, surface finish. On the high pressure die casting of aluminum alloys today, you can get with a surface roughness somewhere around RA 5 micrometers, even lower. So quite a nice surface finish. On the additive manufacturing, when you use powder bed technology and laser, you are usually somewhere around 15, 20 micrometers, the mean roughness or the average roughness. And if you use, for example, electron beam, which is much more productive, much faster, then the surface roughness is like 30 or 40 micrometers, so 2 times worse than using the laser. So it's always some kind of setback. And of course, the basic principle that we reduce the complexity of the 3D object into the 2D by some cross-section means that we always have, or usually have, the object made from individual layers. And the mechanical properties within the layer and between those layers are different. It's about how we can design the process, how we can get rid of this anisotropy. We can do certain steps about it, but still the anisotropy will be present at the final product. So we have to think also, when we are designing the part, we have to think about its use, about its application, how the forces will be influencing our part, and we have to consider this, for example, in the part orientation when we prepare the print. So this is just an overview that every technology we have has some advantages and disadvantages. And it's, I would say, important to speak about both, because basically those 10 years ago, when you heard only about the advantages, then I would say it a little bit slower down the progression of 3D printing, because there was this disillusion, I would say, of all of the, or a lot of the customers. When they purchased the technology, it was quite expensive, and now they realize that, okay, we cannot do everything we thought we could do, because we know too little information at the beginning. So regarding the process of the 3D printing, I will take this just very fast, because the 3D printing itself, we usually see the videos of the printing process, and we usually don't see the other steps of the process, because this is something which is quite significant. It consumes time, of course, and this is you have to pay for these costs somehow. So the first step is we have to create a model. There are different techniques for modeling, different software solutions. I would just leave it at that way. Then we have to take our model, which is parametric, when we have to convert it in some kind of format which can be processed by the printers. Today, the standard is the stereolithography STL file, and we have few other formats like AMF, additive manufacturing format, which is having some advantages over the STL, because usually the STL is only a triangulation mesh. So this is describing geometry, but usually this is not describing material properties, this is not describing surface texture or color. So because we have printers that can alter material properties today, that can even alter the surface texture, we had to have another formats which can, I would say, work with more information. Once we have this STL model, we have to prepare the data in basically some kind of CAM software. In the traditional manufacturing, we have CAD, computer-aided design, computer-aided manufacturing. So the softwares to make programs for printers are called slicers. And then, of course, once we have the data for the printer, we have to set up the printer properly. It's very easy to set up FDM printer. It's more complicated to set up metal printer, for example. Then the process of the print itself doesn't require too much attention for the operators, but where usually a lot of attention is required is the next step. Because when we are speaking about metal 3D printing, the part is usually welded to some kind of base platform. We have to remove it, we have to remove the support, or we have to sometimes finish the parts or machine the parts into the final specification. So I will go just very quickly around these steps because this was intended basically for a very young audience. So this is quite general, but I will focus on certain, I would say, parts which are connected to the metal 3D printing. So the printer itself, usually you are working with the powder materials, which are very small. Those particles are typically from 8 to 50 micrometers, and maybe in the majority of the particles is somewhere around 30 micrometers. At least this is the powder distribution we use in our printer from GE Additive. Because of the size of the particles, you have to take some precautions. So this is sometimes you don't see it in the videos. There are people in the suits basically, and they are working with a 3D printer. It's not, I would say, too safe to present it this way, because the materials itself are causing some health problems. Today we know that they can cause a cancer, so you have to protect yourself properly with some kind of equipment. I would say protective equipment. So all the preparations and all the removal of the part from the printer, you are basically with some breathing system, with some kind of protection, because you don't want to be in the direct contact with the powder. Then there is the other aspect. Few of the materials, typically materials which are having a portion of aluminum or titanium inside. So typically aluminum alloys or titanium alloys are so-called reactive materials, meaning that their surface is quite big when they are in the form of the powder, and they are very easy, or they are very prone to oxidate. And they, of course, they oxidate very fast. So once these materials start burning, it's very difficult to get rid of it. So you have to again keep some rules about the process when you are handling powder, when you are sewing the powder, usually, because before every print or after every print, you have to take the powder in some kind of container with the protective atmosphere. You have to put it into the sewing machine, which basically separates the particles with incorrect geometry from the powder, so you can reuse it. And again, even this sewing machine has to have protective atmosphere, and this process may take you 3-4 hours just to prepare the next batch. So this is something you have to consider. Then the print itself for the DMLS technology is, I would say, very simple. you can see here something which we called island deposition. You can see that the laser is sintering or melting the powder in certain areas. The movement seems quite random, but this is basically intention because we want to have some homogeneous distribution of the heat in the build itself. Because when the heating is only local or in one side of the building pallet, then the deformations are much larger. So this is basically a way how to face the deformations induced by the heat. Of course, the other ways are that you can preheat the whole building chamber. For example, we don't have this option, but when you have EBM machines, electron beam melting, you can preheat the powder bed up to 1000 Celsius degree. And thus you can limit the deformations caused by the thermal deformations. So we don't have the option to heat the powder bed so high, so we need to at least distribute the heat equally. Now you can see the so-called recoater. Recoater is basically a mechanism which takes the powder from the powder container and spreads it with a certain width. Usually the building height we use is something like 400ths of millimeter or 500ths of millimeter, 0.05 millimeter. The process of the printing is usually advertised. It seems really easy, but then comes the post-processing, and we already have some experience with the production parts made by 3D printing, and usually this is the crucial point of the process. If you have correct design, if you have simulated the printing and so on, this is still one half of the way, because usually then you have to finalize the part. And in my opinion, then this is something what the universities are not so prepared. When we are speaking about prototyping production and you don't have basically a room for automation, you don't have a room to make fixtures, to do CNC machining because of the price of the part usually. So you have to do this manually. And this is something which is lacking, or which we don't say too much. When you use, or when you are thinking about 3D printing, you think about the automated process. You take a model, you will put it into the printer, and the final part will come out of the printer. And basically you don't need a skilled operator or skilled worker for anything, or this is at least the general perception. But because the part is coming out, it's welded to the platform, then you have at the final step of the production, now you have a human factor which is introduced there, and usually this can be quite, I would say, fatal for the product itself. Usually the students, or when you have a lack of experience, you are very familiar with the softwares, with the different tools which can help you prepare the build-up, but at the end you have to take manual tools in your hand and you have to finalize the product, and this is usually a place where you can destroy the whole part, where you can waste, I don't know, a week of time of printing. So this is something which is not considered very often, I would say. So the part finishing or post-processing, this is how it comes from the printer. So if the part is this, I would say, very thin structure, topologically optimized, full of supports, and if you design the supports that they can be removed manually, so then the operator can clean the part quite easily, I would say. But when the part should have some better specifications, basically you are aiming for the machining on the part which deformations are half of the millimeter or even bigger. In this case, this is the part which is for some military jet, I would say, here in Czech Republic. This is one of the projects, and the deformation of the part was bigger than 1 millimeter. So you have to use special techniques of programming of CMM machine, because you cannot use the CAD data, because the CAD data is quite different from the actual part that is printed. So you can see that there is a lot of features here which are basically used just for measuring inside the production machine, inside the CNC machine, or inside the CMM, coordinate measuring machine, where you can get some kind of corrections, because you have to understand you cannot program the part using CAD data, because the CAD data is not, I would say, valid anymore. So the part's deformation is much bigger than the final tolerances of the part, and you have to be able to do something with it. So one way how to face the deformation is that you can pre-deform the data you are printing, and you can basically start with the simulation, pre-deform it a little bit, but still this is the way how to get, for example, from 2 millimeters to 1 millimeter or 0.8 millimeter. You will never be within the specifications of hundredth of millimeters, 0.01 or something like this. But because the final products requires this precision, because usually they are not isolated in the object or in the construction, they have to be able to fit somewhere quite precisely, you have to deal with it. And of course, even here, the orientation of the part, you can see that was a little bit influenced also by the possibility to keep it on the platform during the machining, because that's another aspect of post-processing. Usually the design for 3D printing, for design for additive, is very complicated geometry. And we use the full features that really you can have complex shapes. But if you think about the post-processing, then the complex shape, again, you are facing the situation that you have to be able to basically clamp or hold this complex shape somehow. So this is again targeting some kind of special fixtures or using some low temperature melting metals like wood metal or bismuth or something like this, or you have to use the pallet directly, because usually when you are designing the parts for machining, you are also thinking about the fixtures, you are thinking about the clamping. When you are designing the parts for the additive and the last step has to be the machining, you can cause a lot of problems during the design phase if you don't think about it. And then of course the final product, usually you have to inspect if you want to deliver it somehow. So this is the general process of 3D printing, and basically this is also something what we are trying to offer at the university or at our department specifically. We want to have the whole production chain of additive manufacturing, and we are offering this for the companies. We are able to design the part itself, different techniques. We can use topology or lattice optimization. We have tools that we can predict the outcome of the simulation. Basically, we can analyze these deformations, potential failures, collisions with the recoaters. Those are typical tasks that you are simulating, and you can use these results to change the geometry you want to print, basically try to invert the deformations within the geometry. And then of course you have to prepare the build regarding the positioning of the part, generating supports and so on. Within the metal 3D printing, the supports have one property that is very important. Not only they are supporting the structure as in the other technologies, but the powder material has a very low thermal conductivity. This is basically an isolation. So the places that are surrounded only by the powder material can be overheated quite easily. But the supports itself has the same thermal conductivity as the aluminum part. So you can use the supports also to modify the thermal history. We call it the thermal history of the part. So they are not only filling the role of the supports, but they are also helping you to adjust this thermal history of the part to fight with the deformations. Then I would say the print to printer is only a small portion of the whole process. Usually you have to do some proper heat treatment, at least some residual stresses, you have to get rid of those, or a lot of materials you use, you can quench them, you can do precipitation hardening, depends on the material. Then the post-processing, usually when we care about the part, or it goes somewhere where it matters, you have to machine it, because the hand post-processing is not sufficient regarding the precision of the final parts. Then of course we have quite a good equipment regarding dimensional control, surface, texture, and non-destructive testing. Basically, we can use CT today, and we can see the external geometry, internal geometries like lattice structures, and we can also analyze the porosity very quickly. So available technologies, I would say we have a lot of those at the university, but for the metal printing, we have a TruePrint 1000 and Concept Laser M2, which are basically one smaller printer, which is dedicated to IC 316, meaning an inox alloy, and DMLS, which is serving for different materials, because the materials can be changed quite easily, of course, with some kind of other parts that has to be replaced when you are changing material, but this can be done quite easily. So we have printed hot works steel or precipitation hardening steel, aluminum alloys, even titanium alloys, and one nickel cobalt alloys. So we have printed printing parameters for various materials which are qualified. Then we have a lot of polymer technologies. I would skip those. And then we have also some special technologies for additive manufacturing of metals, which are based not on powder bed principle, but one of the technology is based basically on wire and arc additive manufacturing. This is like, you can perceive it like MIG welding, which is on the robot or on some kind of portal. And then the plasma transferred arc, PTA technology, where you can combine materials with very different or with quite different melting temperatures. For example, you can use nickel alloys, cobalt alloys, and you can mix them basically with boron, tungsten, and materials with very high melting points. And using plasma, you can make quite resilient surfaces or even structures on some kind of material which is usually cheaper. Then colleagues here from the university developed a hybrid technology which is called Weld Print, and this is basically an integration of this wire and arc additive manufacturing into the 5-axis milling center. So in one step they can weld part, and the productivity is like 6 kilograms per hour. So this is quite a big deposition rate for 3D printing. So you can place a lot of material and you can machine it into the final specifications within one technology. So this is called a hybrid technology because it provides additive manufacturing and subtractive manufacturing. Then, of course, regarding the post-processing technologies, we have, I would say, other equipment which can be used or which we use to really finalize the parts within the specifications. So this is something that I was speaking about, the strategy. We want to offer the whole production chain, not only the print itself, but the preparation stage and also the finalization stage. So, regarding the principles of different technologies, maybe I can skip those a little bit faster. When I was speaking about wire arc additive manufacturing, just to figure it out, this can be very cheap technology because robots are today quite accessible. MIG welding sources are again quite accessible, and they can, their deposition rate is really within the kilograms per hour. So with appropriate control over this machine, you can have quite a large printing volumes, and you can print with, for example, argon atmosphere. You can even print titanium. So this is a titanium printout using the VM technology. Powder bed fusion, we have already discussed. Now I would maybe aim for the application and maybe for the difference between the direct metal laser sintering and electron beam melting. This is the technology which has a lot of benefits over the direct metal laser sintering technology, because in the aerospace industry, maybe the first aspect they need to solve is material properties, of course. So when they are printing reactive materials, titanium alloys typically for compressor blades, so they are valuing the fact that you can use the electron beam only within the vacuum, and the vacuum itself is protecting the material. So this is one aspect which is quite good on electron beam melting. Second aspect is that you can really preheat the chamber for a very high temperatures, as I mentioned, 1000 Celsius degrees. So then you have minimum residual stresses. And the third aspect over the laser, I would say, when you compare those technologies together, you have usually in electron beam, you have much bigger power. So these printers are using like 6 kilowatt sources. So you can have multiple focal spots at once. So you have multiple beams basically that are sintering the material at the same time. On the laser machines, you have typically lasers 500 watts or 1 kilowatt. And the high tech is that you use 1 or 2 lasers. But yet again, the EBM technology is usually much more productive. It has better precision when you compare the form deformations, because the form deformations are here minimized by the heating, by preheating. But again, the surface finish or the surface quality of the part is much, much worse. The surface roughness, as I mentioned, the parameter RA is usually double or sometimes even triple than on the DMLS technology. So then you have to spend more time on finishing of those parts. So this also comes into the consideration. You can see for the electron beam melting, if you are interested, I will give you this presentation. But basically, what is a great advantage is that you really have multiple focal points at one time, because it's very easy to split the electron beam using magnetic field. So you can preheat the whole bed and then do several parts at once. So the technology is very productive. But on the other hand, you are working with the vacuum technology. You need to have quite a big vacuum. So the maintenance costs and so on is, again, you have to calculate with those or consider those. So this is just a comparison between DMLS and EBM technologies. Focus on our team is basically we are trying to transfer the whole know-how about the process from the design phase up to the inspection phase into the industry. One of our latest applications is basically this brake shield for a military jet, which is a first 3D printed part into the primary construction of the aeroplane in Czech Republic. There are, of course, many other parts printed across the world, but this was the first part which was qualified to be able to install into the aircraft, into its primary construction in the Czech Republic. So these are some parts that we have made historically. I would say usually you see the final part, barely see the parts that are right away from the printer. And you have to consider that usually when the print finish, this whole powder bed is basically at the bottom of the building chamber and it's full of the powder. So only the cleaning of the build plate like this takes you 1 hour, and you are 1 hour within the protective suit. And it's a job, again, very, I would say, human dependent. Regarding the simulation or prediction of the failure, this is something when you have asymmetrical parts or parts with very thin walls, then this comes into the play, because usually what is the most common problem is that the thermal history of the part will deform the part, that it will basically rise above the powder bed. So, and this is the moment where you can easily have a collision with the recoater system. So this is something you have to be very, very careful about, that the part deformation doesn't exceed certain limit, and that these deformations are not coming out of the powder bed, because then they will be higher than the level where you are printing, where you are moving with the recoater, and you can easily hit it basically, and you have a mechanical collision of the production tool. Regarding the inspection, as the CT I was mentioning, this is a very productive technology which can help you gather information about the outer shape, and also helps you to get inspection inside of the part without destroying it. So typical technology for non-destructive testing. Also to mention that all the parts that are printed have some kind of porosity. Usually we are on the level, for example, under 0.1% porosity. But when the printing parameters are not set properly, you can be not on the level of 0.1%, but you can be on the level of single percent or sometimes even higher. So this is SE10 Mg alloy. You can see that the porosity and the defects here, because we have printed it quite fast, so there are pores within the tens of cubic millimeters. And then regarding the application, basically there are two areas where we are aiming: conformal cooling and lightweighting. Lightweighting is aerospace or basically some car racing. Conformal cooling is injection molding or high pressure die casting. So within the Škoda Auto, we have some history of development of inserts into the molds to prevent some kind of problems, porosity problems. So this is basically the conformal cooling inside an insert, which was placed within one part of the mold. Basically, this is a quarter of the mold for the engine head. And the next step, I would say, is this complete piece of the mold. This is 1/4 of the mold already made with 3D printing, with conformal cooling, and already with some kind of experience from application in serial production. And we can say that this, I would say, it has some disadvantages over conform or over traditional materials. So the porosity of the printouts affects the lifetime of the part, and you have to think about it when you are designing the conformal cooling. You have to think about how to repair it, I would say, in certain inspection or in certain periods. So you can make very complex cooling channels, but then you have to think about also possibility of reparation of these channels. So this is basically everything from my lecture. So if you have any questions, you may ask. I have also prepared some model for economical calculation, but I'm not sure if you are even interested in that. So I would like to ask you, if you are interested in anything, you can ask freely. So this is the whole process of this braking shield for one company here, and you can see from the original part, the topology optimized part, the final part machined into the specification and tested in some institution which has a right to test the part for the EASA agency. So
thank you, Libor, for your very interesting and impressive presentation from the demonstrator point of view. Are there any questions from the audience? Please raise your hand if you have any. Yeah, there is one from Jakub from the University of South Bohemia. So Jakub, please.
Okay, so first of all, thank you for your presentation. And actually, I have several questions prepared. However, since we are a bit behind schedule, I will limit it to just.
Sorry for that. Sorry to my colleague.
So first, I'd like to ask, because in plastic additive manufacture, that there is often said that we are basically a bit kind of behind schedule, like 10 or 20 years. And usually manufacturers said that they basically had to wait for some patents to expire to be able to produce some machines for, let's say, hobbyists or even for the industry. So I would like to ask if there is something similar in with the metal additive manufacture. If there are some limitations regarding the patents, or if we are also still waiting for some patents to expire, or how is the situation about this?
Well, take this as some informed opinion. Maybe it's not true, but regarding the polymers, basically it's all about the heating of the chamber, and this was patented by Stratasys, and I would say it overgoes, or it was the patent finished something like 5 years ago, maybe. So now also a lot of producers can make, I would say, heated room or heated printers, which is much better for the quality. Regarding the metals, I'm not sure that there is some kind of limitation. EBM is patented by Arcam. Arcam was bought by 2 years ago by GE Additive again. So there are a few companies who are holding basically these patents, and I'm not sure about any other company who is doing EBM machines, because the laser processing is, I would say, much older. So I'm not sure there is any limitation like this.
Okay, so well, that's quite good to hear, actually. So, and one more question: how is it with the reusability of materials? Because you talked about a few technologies, and again, because I'm more familiar with the plastics. So even with SLS, you have the material degradation mainly to the preheating chambers and so on. So how is it with I don't know, maybe with the wire printer or
so basically the same. When you are speaking about the wire, like wire arc additive manufacturing, you cannot reuse the wire. Basically, when you weld it, then you in the form of the welds, then you only have to put it in some kind of foundry. They melt it and make the wire again. So that's the reusability. But practically, you cannot reuse it. You have to buy a new wire. But the wire is, I would say, quarter a price of the powder. So where we are heading is the recyclation of the powder. That this can be done, of course, and this is done. Otherwise, the economy is nonsense. You have to also think about the supports. This is the same as the polymers. Easily 10 or 15%, 20% of the material can be the supports that you have to remove and you have to throw it away, basically. So this is something when you are speaking about 3D printing, that only the material that you need is used. That's not true, because basically all the technologies use these supports, and this can be easily 15% of the material in average what we print here. So on some kind of parts it can be more, on some parts can be less. But then the powder itself within the chamber is affected basically from the process of the melting, because the process of the melting is very dynamic. You can see the small sparkles coming from it, landing anywhere on the base plate, and basically these sparkles will melt a few particles that they touch, and then these particles will not have the appropriate geometry. So that's why you have to saw the powder after each printing on the sawing machine, where you have some appropriate, I would say, filter that will filter out these particles, but that's only about the geometry. Then of course some reactive materials like titanium, aluminum alloys, you can see that they are oxidating over time. It's very hard to keep the protective atmosphere perfect, not only during the printing, that's the easiest part, but during the manipulation, during the storage, and this is something you have to think about. We didn't record some significant, I would say, deterioration of the material, but maybe we have recycled it just 10 times. That's not too much. And there are studies that are showing that the material properties, usually high cycle fatigue, is getting worse the more you recycle the material. So for the aerospace industry, I know they have, for example, in Avio Aero in Italy, they are making serial really blades into the engines. So it's like a professional serial production, and they have limitations for the recycling. So they have to, I don't know, recycle it 3 times, and then they have to get rid of it. They cannot recycle it all the time. So the use of the material and reusability is definitely not 100%.
Yeah, thank you very much. I completely understand. You know, people are always or very often forgetting with that you are unable to reuse all of it, and so I was just wonder how is it with metal. So
Yes.
thank you very much for your answer.
Pretty much the same.
Okay, thank you. Since there are no more hands raised.
Thank you.
Thank you again for your presentation, and let me introduce the second speaker, which is Veronica Miron, researcher from Institute of Polymer Product Engineering, Johannes Kepler University in Linz.
Hello. Sorry. Okay, perfect. So thanks for the introduction. My topic is actually quite similar, just focus on polymers, and I will try to keep the basics as short as possible and focus on the research of our institute with the focus on medical applications. Actually, the Institute of Polymer Product Engineering, where I come from the Johannes Kepler University Linz, does a lot more. So in general, we deal with product development with polymers, starting from design, construction, over simulations, structural simulations, processing simulations, and also then prototyping, where the additive manufacturing comes in. But we also have other tools for prototyping, and then we also test prototypes or parts that are sent from companies, and we see basically what mechanical properties they have, if they break, if they show fatigue, and so on. And today, first, I'll talk about the motivation, give the overview about the additive manufacturing techniques at IPPU. Then we talk about reverse engineering of anatomical models, as this is an important basic process for creating anatomical models. And then a general overview about the applications of additive manufacturing in medicine. So not just only what we do here, but a really basic overview. And then I'd like to show 3 projects that we did at the Institute. As you can see here, already some outlook pictures. General motivation is that additive manufacturing has rising economic importance. You can see here from the money spent annually in billions of dollars, an exponential growth for the last, let's say, 10 years. And we saw now in the previous talk a lot of expensive 3D printers, but I'm sure that also some of you have some low-cost 3D printers like FDM printers at home. They're quite common for hobby applications. Main advantages we already heard, but as a repetition, for us, mainly the high design freedom is the beneficial aspect. We can create free-form shapes. When we talk about medical applications, we have human anatomy. When we look at this blood vessel of a brain, if you think of conventional manufacturing techniques, there is, to my knowledge, no manufacturing technique that would be able to produce these, as you see it here, printed in one piece. As we also heard before, a lot of support structure was removed there. But this is this high design freedom and the freeform shapes allow us to talk about personalized medicine in the future. Then toolless production can reduce the cost for prototyping and also production of small series. It can even be able to shorten time to market for product development, and it can also shorten production time itself because you don't have to wait for the tool to be manufactured. Now let's get going with the additive manufacturing basic definition according to the standard. It's a process of joining materials to make parts from a 3D model data, usually layer upon layer, as opposed to subtractive manufacturing and formative manufacturing methodologies. And you see here again this complicated shape that you wouldn't manufacture otherwise. So additive manufacturing really has very special applications in this field. The process steps we already heard, so I will just quickly go over them. We have our CAD model. We need to create a printable file, the STL file, standard tessellation language, and then we slice it into the thin cross-sectional layers. Sometimes we need to create support structures. In FDM, sometimes it's possible to also print without support structures. And then the building is happening. And of course, as mentioned before, a lot of post-processing in some cases. So removal of the support structures is one thing, but also for photopolymers, post-curing is necessary often, and in general, sanding, painting to get surface quality that you desire of your small series or prototype usually. We saw before an overview about printing techniques based on the standard. Now I give you an overview based on state of aggregation of the material used. So we start from solid material or with liquid material, but basically you find the same printing techniques that we saw before. We focus today on the wire, so filament printing, fused filament fabrication, also called fused deposition modeling. We can start from film, from granulate. Yeah, it's very interesting for the future, as we might also be able to easily use recycled materials. Then powder-based technique, as also the metal sintering was part of this. We have polymer laser sintering, hardening with binder, or a mix of solid and liquid material. There's this new HP multi-jet fusion technique, which is giving very nice results from mechanical properties and surface quality. And when you start from liquid material, usually the hardening process is with polymerization, curing with light or temperature. And most commonly used here is the stereolithography. We also have the polyjet technique, build a silicone printer, and there are also hydrogel printers. And from the materials you already see here, we are on the softer side of materials, whereas here is more the harder materials that are used. So as mentioned before, these we have at the Institute. So a quick description, fused filament fabrication or fused deposition modeling is the process where we have this polymer wire. Important here is we can only use thermoplastic materials because they have to be remeltable. So this wire is pushed with gears through a heated die, and the die and the platform are moving in XYZ coordinates usually. There are also other systems, but basically layer upon layer, this melt of the thermoplast is deposited. The advantages of this system is that it's quite cheap and it's very easy to handle. That's why it's so common in hobby applications. And the disadvantages can be named the layer resolution, which is usually around 0.1 millimeters. And but that's depending on the die you use. And material selection, well, you can only use thermoplastic materials. And not all of the thermoplastic materials are useful because when they have high shrinkage or the or warpage, then they can they don't stick to the platform, and then you have just a mess at the end of the print. Or in general, when you have a lot of shrinkage and warpage, you have a part that doesn't have the required shape from the beginning. From these systems, we have actually a KUKA robot with this technique on it. We're working on making it work with extrusion also, so that we can print with granulate. We have a large scale, so like a square meter surface of this printer, and then some standard commercial printers from the company Additive and Prusa. Yeah, selective laser sintering. I think before it was quite well described. It's not so much different from metal laser sintering, just that we need way lower temperatures for melting polymers. So again, we have this roller that applies a layer of powder, polymer powder in this case, and the laser that melts the powder where the part should be. And yeah, with this technique, basically we can polymers, metals, and ceramics can be printed. And from the polymer side, we have the options most commonly used are polyamide, polyether ketone, and also elastic materials. This is thermoplastic elastomer, usually thermoplastic polyurethane. And the resolution is usually better than when compared to fused filament fabrication. The disadvantage is it's more expensive. It's a lot more complicated in handling, as we heard before, with the protective gear. And we have only a small selective laser sinterer in the lab from the company Sintrotech. And very nice show models can be produced with stereolithography. It's UV initiated, cross-linking with a laser, or in our case with an LCD screen. Basic material is a photopolymer, usually acrylic photopolymers, but I'm sure that at Profactor there are people that know a bit more about those. And the advantages are speed. They can actually print very fast. We have very good resolution. That's where they're, so coming from a liquid, you always have better resolution than when you come from solid, because the limiting factor is first you have the wire, or first you have the powder corns, and here you only have liquid that can be deposited in a very thin layer on the bottom, for example. And disadvantage is it's quite expensive still, I would say, though there are already lower cost photopolymers now available as well. And there is limited material availability, so there are not that many producers of this compared to filament, where there are a lot of manufacturers already. And I personally don't really like the mechanical properties of these photopolymers, because they are subject to a lot of creep. And when you need a model for a longer time, or when it's under mechanical loading for a while, you see the deformation quite quickly. A bit similar, also based on photopolymers, but also different. The polyjet technology. It belongs to the material jetting techniques, and it's an inkjet printing system. So when you think of an inkjet printer for papers, you know that you can combine 4 different. Okay, my presentation disappeared from my screen. Sorry. That's back.
We can see it still well.
Yeah, thanks. No, it's that the Teams went over my presentation board. Sorry, it's back. Okay, so when you think of your inkjet print head, you know you can print the different colors of materials, and this is similar. In our case, we have the possibility to print with 2 different model materials and a support material, and it's deposited in a layer, like on a piece of paper. It's the material is jetted into D, and then the UV light goes over the whole layer and cross-links the photopolymer. So the advantage clearly is the multi-material printing with the very good resolution. Object says that they offer 20 microns resolution. And you can combine soft and stiff materials. And the disadvantage is the printer itself is really expensive. You have to also use the materials provided by this company, so it's also expensive. And the material, again, it's photopolymer, and for the uses for mechanical applications, you always have to keep in mind that it creeps, and design accordingly or use another material. Here we see when we print with very stiff material, we have a stress strain curve, and the stiff material has very high stiffness here, and the soft material, the Tango Black Plus, for example, is it's nearly horizontal. It's not, but in this regard, you see very, very low stiffness. And then because you can mix the the materials voxel by voxel, as you can also mix the different colors in your inkjet printer, you can get these different stiffnesses. The digital materials is the name for this mixed materials. Okay, and now we come to the last printer I will present. It's our self-put together silicone printer. We use material extrusion as a basic principle. We can print one component and two component silicones that are cross-linked with temperature. We have a pneumatic material feed, and we use commercial printhead from the Viscotec GmbH Viperhead 3.3. So with a continuous piston system. Advantages are we can print with silicones, so they can be very soft to a bit stiffer. They are very versatile material. And disadvantages, currently we have still a very rough nozzle, so we print with layer heights of 0.25 millimeters. We need the pressured air, but we have it in the lab, so it's not that much of a requirement, only if we want to move it. And because of the temperature, so the temperature we induce with a halogen lamp, so it's also coming with bright light, but when it's in the case, it's not an issue either. Okay, let's go to reverse engineering of the anatomical models, because we focus on the medical side today. Before we heard the basic process of getting to the finished part. However, how we get to the 3D part when we actually want to work with existing objects is a process called reverse engineering. So we scan an existing object using photogrammetry, a 3D surface scan, or 3D imaging data, like we know it from the hospital, computed tomography, magnetic resonance imaging, for example. Or then we have the option to design it on the PC, like with standard construction softwares, or we can also use virtual sculpting tools. This is often used by artists. This is also very useful to post-process some STL files. All in all, after we have the scan data, we can then use different techniques like triangulation to create a virtual 3D model, and then go on with the process that we heard before already. Here we see examples when we have a high resolution micro CT, for example. We can even get models from the bone structures. This can also be used for structural simulations, or then in this case we would actually enlarge it to be able to print it with our techniques. There are also photon polymerization, but we don't have those yet. But to get an idea how this structure is influencing mechanical properties, we could now enlarge it, manufacture it, and put it in our testing machines and look at the properties and how well our materials would be suitable to create models for these features. Here you see, based on CT data, skull, and angiography data, the blood vessels, and this is from a surface scan of a hand, but this will be shown later as well. So basically, you see already here examples from magnetic resonance imaging, computed tomography, or angiography data. Angiography is when you show the blood vessels. And you see with MRI that the soft tissue is well visible. However, with CT, the bones come out very clearly. So limitations of this imaging-based design is the availability. You first need to get those kind of data. They're usually coming from a patient or from oneself when you know the doctors and you get the data. And usually there is a risk gain analysis for the patient behind. You cannot just put the patient in CT, and you can also not go there and say, please, I want a very high resolution CT, which might take hours long, because with CT you have the radiation that's harmful for the body. So also in basic clinical procedure. You wouldn't occupy a machine for hours just to see if you can get the model out of it. So it's usually done after hospital hours for research. So it's availability issue. 2D versus 3D means from an X-ray you cannot create a full 3D model. The contrast medium that's necessary for the angiography to get the blood vessel data. It might have also a disadvantage to use it on a patient, so without a reason you wouldn't give it. And recording time already mentioned, which goes hand in hand with the layer resolution and the contrasts. You don't see in every picture everything. So depending on what you want to model, you have to choose the right image data. And we saw bone, brain, and blood vessels we can see in these pictures. However, the hair or the arachnoidea, which is one of the brain skins, you don't see in any kind of data. So you have to think how else you would model those if you need a virtual model from these. And another issue is the segmentation. There are a lot of automatic tools already available. However, you have to check if they give you the right precision and if for the right feature you have the tool available. And for manual segmentation, it can be really tedious to mark in each layer the region of interest. But when you have your model, you can talk about additive manufacturing for medicine. There are different areas of application. I found this overview very nice from Gulmon 2019. And they basically divided it into bio and drug-based additive manufacturing and polymer metallic and ceramic-based manufacturing. And we start with the bio and drug, just a short overview, because this is really not my topic normally, but for the purpose of having really the title not cut short, this is good to hear, and it's usually in the news, so just to give you a short input. 3D organ bioprinting, as it's often in the news, regenerating medicine. I can tell you what I found is that already transplanted are bladders and urethra, blood vessels and ears. So you can see here examples. And there are two options. Either they print a scaffold and they put it in the incubator with the cells that should grow in it, or there are also printing systems available that print the cells directly. However, not transplanted yet and still very much in research is the organs, kidneys, lungs, heart, liver, so the full organs. And they're very difficult to manufacture because you have usually not just one type of cells, but a lot of different ones. And it's also a complicated 3D structure. So you need first a very high resolution imaging data, then you need the segmentation. And even when you have that, you still need to be able to fabricate it in all these different materials. When we already talk about macroscopic multi-material printing, we come to our limits, but dealing with biological materials, it's another challenge. And for drug delivery systems, it's also quite a nice application, I would say. Basic principle is that with the internal density, because you can change that with a 3D printer very easily, it allows to control adaptable drug delivery. So yeah, the more surface, the more drugs you would be able to release at the time. And it also can dissolve with time. So yeah, a lot of different options there. Now coming to something I'm more familiar with in everyday life, polymeric printing. Here, basic overview, you can print lab and test equipment, assistive tools, orthoses and prostheses, implants, training and surgery planning models. Here the anatomical models come in. and instruments for diagnostic and surgery. So before we saw the Gartner's hype curve, which is very interesting because very far along this Gartner's hype curve, really out of the valley of disillusionment already, and very well applied is 3D printing of hearing aids. This is really a good example how the technology can be used also for mass production, for mass production of personalized products, because every year is different. If you need different shapes, and the process that this company Videx presents is they have a standard order intake, scan the model, they do the modeling, printing, mounting, and polishing, and it's a very very standard process and really yeah, well applied already. The second most common use of additive manufacturing is in medicine, is printing for dental applications. Here, some of you might already be familiar with these transparent liners. These are not directly printed, but these are thermoformed based on top of 3D printed dentitions. So basically, you have the dentition virtually changed to until you, so every 2 weeks or something like this, you get a new model, and those are printed, and then the thin liners are thermoformed on top of these molds. And so every, let's say, these 2 weeks, you put the next shape on your teeth, and they push the teeth in the right position. Also, crowns can be 3D printed. Maybe you can also have implants. Here, quite interesting, and I didn't mention it in the presentation, but there is this very interesting EU project, Inkplant, where Profactor and our institute are, amongst other partners, part of, and the aim is to produce 3D printed implants. One of the use cases is for exactly this application. And I saw somewhere that Litos will present in one of the next talks, and these are actually printing crowns like this. So a very interesting talk to come probably. Yeah, now we are at 3D printed anatomical models. They can be used for very lots of applications. Can be something simple like parents wanting a model of their fetus based on the ultrasound. So there are companies that have this as service. But in clinical use, it can be used for, so you have a patient model and the doctor goes to the patient and their family, and they can explain complicated surgeries and what they're doing. And this is usually easier when you have something to show and to touch. So it's easier to get informed consent from patients for complicated surgeries. It can be used as a study aid for anatomy. It can be, I don't know, medical students or pupils. Basic surgery planning. You can choose a trajectory or the tools. For example, later we'll talk about aneurysms and aneurysm clips. And those have to be chosen with regard to the patient's anatomy. So when they have the right model printed, there are a lot of studies with the use of these anatomical models of these blood vessels. They have shorter surgery time because they can choose before the surgery already the trajectory and the clips. So it's faster in the operation room. And in general, it can help making decisions and also team trainings. There are also 3D printed bone implants, as you see here from the years. It's there should be already some more since 2014, but basically I found skull implants from PEEK, polyethylene keton, so high temperature, high mechanical properties polymer. Then a jawbone from titanium, so metal printing, intervertebral disc, tracheal splint, and shoulder joints and hip joints. So I'm sure that with the research going on, there will be more in the future. And here also the implant project comes in. And for orthotics, this is actually useful when you have a 3D printer at home. And in this case, it's a nice story. A colleague went snowboarding and he injured this joint. And with a common medical plaster or orthotics, he would not have been able to put on gloves again and go snowboarding again. So what he did is he scanned his hand, designed in some iterations 3D printable fixation that is fixed with double-sided duct tape and medical tape onto the skin. And what it does is it hinders the middle finger to be moved, but he can still wear gloves. So very lightweight, does the basic job, and actually with some special features that it doesn't, so it also allows the movement of the hand. So this curvature changes all the time when you move the hand normally. So there is anisotropic bending flex features here. And also on the bottom side, you also have some soft material on the inside to have better haptic properties, more comfortable. And there's a lot of research on this automatized generation of hand orthotics, like this, hand splints like this, also with some cushioning regions or flexible parts and stiff parts, removable, and so on. I think the advantage is quite clear. You can take it off or you can go and wash, and it's still air on a lot of the surface while keeping the fixture. Now, I'll show you 3 of our projects. One was the development of personalized mouth sticks in the project RapoErgo, Rapid Prototyping for Ergotherapy. Basic explanation, what is a mouth stick? It's for people that cannot use their hands or arms, most often quadriplegics, but also when you have spasms, for example. And they're called by the users themselves the Swiss Army knives amongst assistive devices, because they use them in a lot of applications, for example, signing, typing on keyboards, touchscreens, turning pages in books or magazines, or doing even handcraft like braiding. You see here, one of the project partners actually braided a full basket with this mouth stick. And he's also programming 8 hours a day, so really without the mouth stick, would be very hard to be independent for him. Yeah, the objective of the project was to find the user's needs, so to really make personalized mouth sticks possible, creating a web-based design tool that the users can design their personalized mouth sticks, and that can then be fabricated, half automatized. And for this, we also developed 3D printable personalized mouthpieces. And very often I use this basic separation between direct additive manufacturing and indirect additive manufacturing. Basically what it means is either you directly print the mouthpiece in this case. So you have for each mouthpiece the possibility of changing the geometry without creating additional costs. And we did some basic studies for stability. And for indirect additive manufacturing, it's also called rapid tooling. 3D printing of molds is the meaning. Here we created an injection molding tool using the Objet. And we also did some manual molding with single material, where the adapter for the mouth stick is already included as inlay. This was silicone used here. And the sandwich structure was also tried with an inside hard structure and outside soft, so sandwich structure molding. The advantage of the direct printing is that you really have the ability to print individual shapes, and as this was the goal to really, each mouth is different, so a one-size-fits-all approach was not really applicable, but still for mass production, as it would be a case with injection molding. You're limited to this one shape per mold only because, well, the mold is like it's looking like, and this is the shape you're limited to. So the more pieces you want to manufacture of the same geometry, the more the cost balance would indicate that you should make a mold and produce it. Also, with the molding, back then we didn't have a silicone printer. This was the only way to also try silicone as a material. However, that was either way too soft for the people, so they really wanted this. We selected then medical grade thermoblast. We created filament and optimized the printing process for this filament, and that was the final version that the users were also satisfied with. Coming to the next project, the development of a non-invasive patient fixation device. It might look a bit weird, but it has a very good reason why in a hospital somebody would be fixed with the head to the table. During radiotherapy for tumors in the head region, the patient's head really needs to be fixed in position with high accuracy, and we talk about maximum of 1 millimeter movement in all directions so together, because the techniques for targeting the tumor get better and better. But if the patient moves, you have a lot of region with healthy tissue that the radiation might hit. So as the healthy tissue needs to be protected, the patient needs to be fixed with high precision. The current process is with this mask, as you see here. You have a thermoplastic net. It's usually a polycaprolactone material that's heated in a hot water bath. And it's consisting of 3 parts on the bottom, and then 2 on the top, 1 without holes, and then the mesh. And it's just thermoformed on top of the patient's head, and this can create discomfort during the molding process. The whole process for this type of mask is about 1 hour. And during the cooling and the hardening, there's also shrinkage, which additionally is described as not that comfortable by the patients. Eyes, mouth, and nose are usually covered. So if there is really a problem, they cut out some holes. But I tried it, it's really not comfortable. And especially if you're claustrophobic or children are patients, then it's really not nice. And the objectives for the new mask is higher patient comfort in the first place, but for the therapy, of course, the most important thing is to have the same or even better fixation performance. And always an issue in medicine is also the cost. So as the current system works, it should have the same or lower costs. And we used proband. So in our case, we designed the masks based on MRI data, but it would be also done based on CT data. And we have the segmentation of the head. Then we transform this imaging data, as we heard before, based on the grayscales. We select the region of interest, and then with polygonization, we get the STL file. Then with some post-processing also of this STL file, whoever already dealt with it knows what I'm talking about. Can be also sometimes time-consuming to do this. And then we did designs, as we wanted to make it very similar designs. We used templates that were loaded in. Then the head shell was also imported in several softwares. We, in the end, used Siemens NX, Frematic from company Materialize, and also Blender for the last final smoothing, which could also be done in Frematic, but preferences. Then about manufacturing, there was a printer selection with a closed building chamber because we wanted to use ABS, as a lot of literature research resulted in the fact that this is a very good material for this case. needs a heated platform then to print this ABS in the first place, and a platform size that's large enough to accommodate this big mask. The print accuracy was evaluated using reverse engineering with the GOM ATOS system. So it was scanned optically and reverse engineered, and then overlaid with the previous original STL, and the differences between the original and the printed file then was analyzed. And for the printing, we did some process optimization to reduce the amount of support structure that's necessary to print. As you see, the whole inside here needs to be supported. In this case, we use breakaway support. And the process was splitted also to reduce support structure necessary. We also did some analysis, as it can be quite rough printing structure for this purpose. You also reduce print time and so on. Yeah. What we did then, to evaluate the accuracy, the scan-based design of fixation device, and here you see the fixation device that fits in the MRI head coil, because we did the evaluation in the MRI. We used 4 healthy volunteers, 2 male, 2 female, and for each of these volunteers, 3D printed mask was created, and a conventional stereotactic high precision mask, so this net-based mask was created. And then in a longer, the whole measurement took around 1 hour. MRI evaluation was split in 2 sections. One was the base MRI, where the proband was told to lie still, not move. And then there was this movement measurement, where over a mirror, here you see the mirror shows a screen, and from the screen over the mirror, the proband read commands like move left, move right, rotate, and so on. As results, we got a lot of curves, translations, X, Y, and Z, and rotations around X, Y, and Z, plotted over the time, so over this measurement time. And to simplify these results, you see here in blue is the standard, and in magenta is the new mask. And you see here for the absolute 3D displacement is on the y-axis and the time on the x-axis. And you see here for the 3D printed mask, the probands barely could move, whereas here there's a lot of jitter already here and the drift over time. So when they relax over time, they have a lot of freedom to move already. And the relative 3D displacement, so to the average position of the head, also again for the magenta one is the 3D printed mask. You see the movement, the displacement is always lower than for the conventional mask. And the same is if you look at the maximum leeway, so absolute movement maximum over the whole time. Again, magenta, the 3D printed mask, allows less movement than the standard mask. So overall, what we could show is that the mask design based on MRI data or CT data is possible. We have the ability to leave eyes, mouth, nose uncovered. The proband cell was more comfortable than the currently used mask. However, with 4 people, needs a lot more people to do the study to be able to to use the subjective feedback. And overall, it shows better fixation performance than the conventional mask. Of course, there is always future work to be done, but we go on to the last project that I want to show you. And it's actually Upper Austrian's largest medical technology project. funded by 3.2 million euros. And we are a lot of partners of a lot of disciplines. The project is called MEDUSA, Medical Education in Surgical Aneurysm Clipping. And the main goal is to develop a surgical training simulator with the challenge of surgery for aneurysms. Aneurysms in the head region, so we talk about cerebral aneurysms only, have a prevalence of 3 to 4% in the whole population. The elder population is a bit higher. And as long as you only have an aneurysm, you can still be fine. You might not show symptoms. However, if it ruptures, it's a problem. And then you have subarachnoidal hemorrhage. There's this arachnoid that was mentioned before, but you don't see on imaging data. And with this ruptured aneurysm, so some patients die directly, and some have very strong physical and mental implications, and only a third has the same life quality as before this bleeding. In this case, a surgical intervention is definitely necessary. However, sometimes before an aneurysm ruptures, it can be discovered at standard checkups. And there are two preventive treatment options. There's this option of endovascular coiling. So you can see here in the picture where through the leg, through endovascular, also through the blood vessel up until the brain, then the aneurysm is occluded. However, if in cases where this is not possible, there is open brain surgery necessary. You see here some pictures of an open brain surgery, where you see here the aneurysm. This is a very complicated procedure with a lot of steps, and it needs some training. Nobody really wants to be the first patient to be operated on by a surgeon. So it's good if they're well prepared. Of course, there's a lot of training in the surgery room. However, all surgeons actually prefer to first have an impression of what they're dealing with before first time going to the patient. So what we want to do is give them the option to simulate this in a safe environment. There is virtual simulation. It's basically like a computer game. In our case, the virtual part of our simulator, because we want to make a hybrid simulator. In our case, the intention is that the surgeon can use from tomorrow's patient the imaging data, put it in the software, do automatic segmentation, make the operation planning, have the clip library with which the occlusion is happening, and be able to perform the clipping, and then afterwards check how well the occlusion was performed. So we have this blood flow analysis, which shows if there's still blood going in the aneurysm, which should not be the case in a final surgery. Basically, it allows the surgeon to prepare. It allows already students to train with standard cases. And well, there's this saying from, I don't know whom anymore, but chance favors the prepared mind. So surgery outcome is better if you're prepared. And there's the real world with the haptically realistic bench models. Now this is from one of the first months of the project, so it's looking a bit different now. But basically we have soft skin, hard skull, moving brain lobes, and the arachnoid, and blood vessels with the aneurysm. And these two worlds, virtual and real, are combined with the hybrid world, where the surgeon sits there with a VR headset, like they would look through a microscope. And there's a tracking of the real surgical instruments. So the surgeon doesn't use some haptical tools, but the real surgical instruments to do this simulation. And then there's augmented reality to see the real world and overlaid so the virtual world overlaid with the real world. Our institute deals with materials and manufacturing processes for the real models. Then we did some material analysis, and you see here is young modelers over density, and you see blood vessels, and especially the brain is really one of the soft materials that are given somewhere. And as artificial materials overlaying are some soft hydrogels or silicone rubber. As you see here, they are very versatile in their application. And again, we have the separation between direct and indirect manufacturing. The 3D printing of the models. Here we have another division between the soft models. Here we see the 3D printed brain model and some hard models just to show what we are doing, just to study some anatomy. And 3D printing of molds. There is this fluid injection molding, in this case manual fluid injection molding, to create some hollow blood vessels, and the manual molding with dissolvable molds. Can use here, so 3D printed ABS, for example, is dissolvable in ABS, and PVA, so polyvinyl alcohol, is dissolvable in water. And those were used in this case, for example, to create models and then coat them with silicone or latex and create these hollow models to have a basic study of anatomy and material properties, how well the surgeons like the representation and so on. And then there are also separable molds that you can reuse in the end. The advantages are again the same as mentioned before, with the individual shapes versus the one shape only with the molding and the number of pieces manufactured. In summary, coming to the end, additive manufacturing turns out to be very helpful in the development of medical technology. They can really improve team communication in the project as well, as when you discuss about the topic that, let's say, medical topics and a lot of engineers, to find the common vocabulary, it's easier to show on a model very often. Also, prototypes can be produced rapidly. It's a big advantage in this case. And to create freeform shapes or in general parts in low numbers, it's we already had it. It's very beneficial. Important is I didn't mention this before, but the medical regulations, they have to be taken into account from the beginning of the development on. And interdisciplinary teams and the participatory design principle really improve the outcomes. With rising economic importance and the high design freedom and the toolless production, I'm sure that the use of additive manufacturing will not come to an end very soon, but we'll find a lot of new applications that benefit from this technology. And I personally see current and future research in this topic, actually in 3 topics: the optimization of the printing technologies for very soft materials, and optimization of mechanical properties of parts and materials for standard applications and printing techniques. So mechanical properties, that was mentioned before as a disadvantage of additive manufacturing in the last talk. And additive manufacturing with high strength, high temperature polymers, which is, again, a very different research topic than for the soft materials. A lot of people contributed. I'd like to say thanks, and to you, thanks for the attention.
Thank you, Veronica, for very interesting presentation. I know the institute in general. Professor Miron, of course, we met several times, but from such broad point of view, I haven't seen such presentation so far. So thank you for that. It was very interesting. So, are there any questions from the audience? Maybe before somebody is encouraged to raise his hands, I have a question. biocompatibility of materials, because a lot of materials or a lot of use cases you mentioned are basically in direct skin contact, or you can directly put it in the mouth. So how is it with biocompatibility of your materials?
Well, they have to be, it has to be considered. Of course, biocompatibility is dependent on the time and the region that it's used. So skin contact is quite easy, I would say. If you use certified material, and you have also in research is even easier for certification. But in general, you need to prove the biocompatibility of the finished parts. So in our case, we used certified materials, and we printed it in a very clean environment, and that was sufficient for our research. However, of course, if that would go in mass production, it needs certification. But for the mask, especially, it's we are not that far that we have already applications on patients. So this would still be the next step. We only used probants so far. And for the simulator, the only thing that makes it a medical device is when the surgeon uses the tomorrow's patient data as for surgery planning. Until then, when it's only a training of standard cases to learn, and it doesn't have direct patient connection, it's not a medical device. And they wear, they have the surgical instruments, and they have to wear gloves because they simulate the surgery. So there's also no skin contact, but silicones are certified for skin contact also, and we take care that it is not harmful for the trainees, of